It is 12 o'clock, and it's my pleasure to welcome you to the fifth installment of this year's biomass webinar series. The webinar series explores how perennial biomass crops and emerging supply chains can support resilient agriculture, sustainable manufacturing, and regional economic development. It's brought to you by the Center for Advanced Bioenergy and Bioproducts Innovation, the Diverse Corn Belt Project, iRegen, and the IFAB Tech Hub, which are all associated with several organizations that are part of the University of Illinois and Iowa State University, and sponsored by the United States Department of Food and Agriculture, the Department of Energy, and the Department of Commerce. Next slide, please, Michelle. Thanks. So today we are visiting with almost Dr. Bryan Petersen. He's a PhD candidate at Iowa State University. Bryan's going to be talking with us about how we use models to understand what we know and what we don't know about Miscanthus so we can understand where it can grow better and how we might breed it to grow better in the future. And then next week, sorry, there's a typo on this one, but next week we'll be joined by Ty Miller, the senior utilities engineer at the University of Iowa, talking about the biomass fuel project they've had with Miscanthus there for the last 10 years. Next slide. I'm delighted to make the announcement again about the first International Miscanthus Summit that's being hosted at the University of Illinois. I see Steve Schomburg turned on his camera. Steve will be there, or is planning to be there at least. I want to make you all aware that abstracts are now open for submission, whether that's for contributed presentations or for posters. Abstract submission is open through August 10th. So please register and submit your abstract. I can't wait to see what talks are contributed. And with that, it's my pleasure to turn things over to Bryan to tell us about how we grow Miscanthus in a computer.
Thank you, Emily. Thank you for the introduction. The other things I'll add is I'm being advised by both Dr. Emily Heaton and also Dr. Andy Van Lukey. So this is my PhD dissertation is essentially about trying to improve some of our capabilities of modeling Miscanthus. So I'll try to give you all a rundown of how do we grow Miscanthus in a computer, which is just modeling it, and with a focus on Miscanthus here in the Midwest. Okay, so I'll start you all off with a hypothetical scenario. So imagine you're a farmer in central Iowa, and they're considering planting Miscanthus on some land that doesn't produce high corn and soybean yield, some marginal land. They ask the obvious question, how much is it going to yield on this ground? Are they going to be able to make money off of it? And they can answer it two different ways. The first option, if there's no yield trial nearby with no historical data, they would have to try to perform a trial on similar ground, and they would have to wait probably 5-10 years to get that yield data. Hope there isn't a big flood or drought or extreme weather event that may not be representative of the average climate. And if that trial fails, meaning that it doesn't yield enough to be successful, they've already spent a bunch of money performing the trial, and even if it does succeed, that market demand for the crop may already be gone. So the other option, hold on, oh, there we go, is to grow it in a computer or model it. Then you can run thousands of simulations across different weather management scenarios, potentially in just an afternoon. The simulation would give you an expectation of, and maybe a sense of uncertainty around what the crop would yield without waiting 5-10 years or putting some land in production already. So this type of hypothetical scenario highlights one of the reasons of why we would model commercial Miscanthus, Miscanthus. It can support decision makers to optimize management decisions. So that was one of four. Um, the this well, these reasons why you would model a certain crop were actually developed from Piao and Matthews, some colleagues at University of Illinois that just recently wrote a review paper about this. So one of the a more high level example of using a crop simulation model was to is uh, pr produce this figure in Fan et al. 2024, where they were looking at where can they plant Miscanthus switchgrass or energy sorghum that would optimize certain things. Another reason why you would want to model Miscanthus is you can see how it is impacted by changing climate. I couldn't find an exact example in the literature for Miscanthus, but this has been done for commodity crops over the past five years, where they've looked at changing the atmosphere CO2, the temperature, and seeing how that affects global yields. The other reason why you can use crop simulation models to identify targets for crop breeding. So just this past year, Audie Carroll was looking at different um, genotypes or different cultivars of Miscanthus, and they used the crop model to simulate 10 years of growth under these using these different genotypes, and found that the one that performed the best was actually not the didn't have the highest potential, but it was the most resilient um, to droughts. Fourth, you can then you can also use crop simulation models to try to improve the environmental sustainability. So here's an example of where they saw the effect of changing the harvest date and seeing how that impacted the greenhouse gas emissions um, from the crop. So in this presentation, I'll get into more of the details of what exactly is a crop simulation model, or CSM for short. How do we specifically model Miscanthus? What are the current capabilities? And then where are we headed? So every CSM, no matter how complicated it looks, it has the same basic structure. So I find it easiest to explain with something that most of us already have an intuition for, and that's an American football game, not an actual football game. Um, so, except most of us have this intuition. Iowa fans are still trying to figure out how they keep losing to Iowa State. But anyway, you got a playbook with a play call that's executed. You've got a game state, which is the score, field position, down distance. You've got external conditions, the opponent, weather, crowd, penalties. And every play takes the current game state and runs it through the playbook under certain external conditions, which produces a new game state. It's a kind of like a loop. So you drive up, and then the playbook makes a change, and then that change is then used in the next iteration. So this is the entire architecture of a crop model. So an example for a crop model would be to have weather, light, temperature, rain as external drivers. And then the playbook would be mathematical functions or equations that represent different things, such as photosynthesis, respiration. Um, these this is the the guts of the model, and it's important that these functions are based off of data that we have collected, or how we've seen the crop grow. So, for example, we know that leaf area index is linearly related to accumulated temperature. Um, And then those functions can then update different states, such as the amount of biomass, leaf area, soil, water, temperature, plant nitrogen, those sorts of things. So going back to Piel Matha and Matthews, they actually provided a nice diagram that can show the complexity of each model. So the playbook, there can be a lot of different plays because there's a lot of different things that we need to represent, such as the changes in phenological stages, or what stage the crop is in, how that affects evapotranspiration, or how much water is being lost, how much carbon the crop is taking in. So instead of trying to unpack this all at once, we'll talk about an actual Miscanthus model, starting with the Miscan mod, which was the first CSM built specifically for Miscanthus. It was built back in the early 2000s when they had a bunch of field trials across Europe that saw that Miscanthus could produce very high yields, but they did differ from place to place. So instead of taking just the average and saying that the EU could produce this much biomass on this much area, Clifton, Brown, Stomfel, and Jones used that data that they've collected on how Miscanthus grows and put that into and wrote that into equations to try to predict what the yields would be across Europe. So they saw that solar radiation, air temperature, and precipitation um, were important in predicting Miscanthus yield. So using data that they've collected back in the 1990s, they saw that as leaf area index increases, the amount of radiation that the crop captures also increases with diminishing rate returns, and they fit an equation to that, which this you'll sometimes hear model parameterization. That is model parameterization, fitting in a line to the model. So based off the amount of light, they also noticed that as that intercepted light is a certain amount of biomass can then be gained from that. So they saw as the PAR increased, they saw this pretty linear relationship in terms of above ground biomass. They actually found that approximately 2.4 grams of grams of dry matter per megajoule of light intercepted was a good approximation. They also included water limitation. We won't go into super big detail about that. The main takeaway is that they use external drivers, so radiation, air temperature, and they took their understanding, what they saw in observations, to build these functions that update that can be used to predict above ground biomass, leaf area index. So this is what they found. This top map assumes that the plant was irrigated and doesn't experience water stress, so you can see a north-south gradient in yield potential. It's higher in Southern Europe because they receive more radiation within a growing season. However, the water stress would prevent actually those southern locations from reaching upwards of 50 megagrams per hectare, and as you can see shown in the lower map, you notice these small yellow dots. These represent Miscanthus yield trial locations that were spread across Europe. They used the data from this to evaluate or to see how well Miscan mod performed. And on this left figure is a scatter plot with predicted yield on the X, observed yield on the Y. Each point represents a one of those yellow dots. Um, it also should be noted that the observed yield from these locations was the peak yield, not the yield when the miscanthus is normally harvested. The black line is what we call the one-to-one. So if Miscan mod was perfect, all the black dots would line up on that line. However, they don't, and that's associated with the error. So you can see up here, 5.65 is the root mean squared error. So you can expect that Miscan mod on average would be off by 5.6 megagrams of dry matter per hectare. Pretty good though still. That error can be decomposed into three different things, which can tell you a lot about the a model. I won't go into super detail, but the having a low bias is good because there's no systematic error in the model. So I tried running it Miscan mod over the same way that Clifton Brown did in 2004, just over eastern Iowa, where we have some commercial yield data just to see how the model performed. And you can see the root mean square error doubled. Um, so the model systematically overpredicts yield here. Why? Well, it could be for two reasons. One, it could be errors in external drivers, or it could be errors in the functions themselves. I I thought maybe that um, I used the half a degree gridded weather drivers. I thought maybe that's too coarse. Maybe it blurs some of the real field level variation. So I ran the model with more field specific drivers, like differing soil. But overall, that didn't improve the model at all. So what's actually is missing is, like I said before, Miscan mod was evaluated using peak yield, not harvest yield. So Miscan mod doesn't account for senescence or harvest losses. So right now we can assume that, or there's published estimates of that there's 40% of the above ground biomass is lost in senescence, and then 15% maybe is lost at harvest. The phenocandidate imagery can show exactly that. You can see that here early in November, there's a bunch of leaves. Later in March, when it's harvested, not many leaves. Um, so applying that correction improved the model quite a bit. Now the root mean square is 4.8. But it still didn't capture the variability seen in the observations very well. So this little exercise just shows the importance of knowing how the crop simulation model was evaluated to make a prediction. Okay, so what are some of the current capabilities of Miscanthus CSM? So in order to build a model, you need to have data to support those equations that you use. So essentially, we're asking, what do we have good data on? First thing that we have good data on is how Miscanthus advances through different stages with time, or with, as we see, it's not through clocked like a physical clock, but through a temperature clock. So this model uses temperature thresholds. So as the thermal time, I'll use thermal time is essentially just temperature accumulation. As that increases, you can see the model steps through these different thresholds where then the model can make different assumptions. So as it increases, it goes through emergence where the above ground dry matter can then start to increase, and then gets to leaf expansion where a lot of that carbon will be allocated to leaves, and then once it reaches a certain point, then leaf senescence starts, and then that allows the model to say, okay, all this light that we're getting is not being used to increase biomass. And then after a certain point, then we have full plant senescence where we have a decline. So that essentially allows us to better figure out the harvest, um, um, how much biomass is left at harvest. So these are the different stages shown in this phenocam. Here's leaf growth, you can see, and then senescence, leaf senescence, fully senesced. Next thing is we do a pretty good job of predicting above ground growth, um, because we've collected a lot of data on measuring the total above ground material and also how much light is being intercepted just using a simple sensor above and then below the canopy. We can figure that out pretty easily. And from those two measurements, we can get at this what we call radiation use efficiency, the ratio of above ground dry matter produced per amount of absorbed light. A bunch of models you do it this way to predict above ground growth. However, it is you have when the plant becomes stressed, you have to reduce RUE by how much? It's hard to know exactly. So that's kind of one of the current limitations of doing it this way. Another way of doing it is using a more advanced model of photosynthesis itself, where we can essentially uh, use enzyme kinetics or how fast these molecules are working to assimilate carbon in tissues. So this way requires a lot more data um, to get right, but uh, but we are able to collect it fairly easily. The other thing is being able to predict how much how does Miscanthus ultimately change the water cycle. So we have measurements of fluxes of water, such as what we call evapotranspiration going from the plant to the atmosphere. And these models are built around data from these, what we call eddy covariance towers, to scale it up to regional estimates. So Van Lucke et al. 2010 did this using a CSM, where he found that if we were to plant Miscanthus across the Midwest, it would increase that water loss from evapotranspiration by almost 200 millimeters per year. But it would also decrease drainage, which has nutrient loss applications. Um, and that can be taken a step further in models if you couple it with a weather model to how to see Miscanthus's effect on the climate, which he 2012 or 2002 2022 saw that it could planting Miscanthus in the Midwest could reduce summer temperatures by almost a degree Celsius. Um, the other thing that we have a somewhat good handle on is nitrogen dynamics within the plant. So how much knowing we see that there's not a whole lot of Miscanthus is not very responsive to nitrogen fertilizer. Sometimes it is, sometimes it isn't, which can be because it is essentially banking nitrogen in its below ground structures, the rhizomes, as seen here. And people have come up with a model for how it how it moves these available, or we call metabolic reserves, or available carbons and nitrogens that can be used to produce above ground growth. Um, exactly how much available carbon and nitrogen in these rhizomes um, is still not really known very well, and when and how much carbon and nitrogen is being moved to produce above ground growth is still kind of unknown. Um, but that is an area of further research. Okay, so what are these or where are these models headed, and what's still difficult? I talked briefly with the plant nitrogen dynamics is still hard to resolve in these CSMs. These next two slides aren't comprehensive. This is kind of what I'm working on. Um, so one of the things that is not represented in CSMs is the residue physics. So we see as Miscanthus senesces, it drops most of its leaves, and that creates a mat of material that can build up over time. Um, and actually, it can be removed for additional biomass. But this material here can buffer soil temperature, soil moisture, which can change the environment where the rhizomes are living, which can impact uh, the um, the health of those rhizomes. So um, I'm trying to integrate these energy physics into a Miscanthus CSM. Um, and when I do that, you can see in this below image, this above figure shows the difference between model and observation. So red means the model is warmer than what the observations are saying in the soil. Blue means it's colder. You can see 2019 is when we established the Miscanthus. The difference is not very great, but as the Miscanthus ages, and as that litter or as that residue layer increases in depth and mass, that bias or that difference, especially in the edge seasons where Miscanthus is not growing, um, can be is can be pretty high, upwards of 10 degrees Celsius. Now, if you now assume that there's this insulative material above the residue layer, um, if we have that on, that greatly reduces those differences. And this can have implications for uh, soil carbon accumulation, because as soil temperature and moisture are very important for soil carbon accumulation. As temperature increases, typically you see more respiratory losses in soil carbon, which would change a bit essentially the greenhouse gas predictions from these CSM. So that's one of the areas of that I'm currently working on. Um, One of the other things is that just recently, Emron, one of Emily's research scientists, was able to develop some remote sensing tools to essentially allow us to see Miscanthus variability at a spatial resolution that we've never been able to see before. So these panels show different commercial fields here in eastern Iowa and their yield variation. You can notice that there are certain areas in the fields where, especially in this lower left field, where there is lower productivity than others. So why is that the case? We don't exactly know. Um, one potential hypothesis is that these low yield areas simply have less rhizome biomass, um, which uh, prevent, which cannot support a whole lot of above ground growth. Those below ground biomass reserves um, could have been a result in like a one-time event where like maybe winter kill killed some of the rhizomes, which left the stand at reduced capacity for future growth. Another possibility is that just the environmental itself is a limiting factor. So maybe soil properties such as water holding capacity um, with um, with little precipitation could have reduced productivity, above ground productivity, regardless of how healthy the miscanthus is, or regardless of how healthy like the rhizome system is. Third, which probably may be the case, is it could be both that they interact. That environmental stresses could gradually deplete these underground reserves of carbon and nitrogen over multiple growing seasons, which create like a, a feedback where stress plants become progressively less productive. So knowing these mechanisms are important because they could have management implications. So if the limitation is like because that the rhizomes aren't healthy, um, you could have you could do some interventions such as replanting or potentially tillage to promote rhizome recovery and potentially increase yield. However, if like environment was the limiting factor, increasing rhizome biomass again maybe wouldn't produce any sort of meaningful gains. So this lower figure is show our lower picture shows Heather Roney, she's a PhD candidate being advised by Dr. Emily Heaton, and we've been or they've been doing measurements of above ground biomass, rhizome biomass, root biomass with and root ingrowth cores, which that data I heard is just now in, which is very exciting stuff across these different productivity gradients. And hopefully our goal is to like integrate these measurements into a crop simulation model to estimate the carbon and nitrogen fluxes that are we are not able to measure directly, and then we can potentially use that the model to begin testing these mechanisms of why we see this subfield yield variation. Wrapping up, going back to the four questions. So a CSM is just essentially a set of equations that uses management environmental variables to predict different things such as biomass. How do we model it? We can do it in a variety of different ways. It just depends on what data we have to develop um, the the model. And three, what are the current capabilities? Um, I think we're really good at estimating above ground growth at a regional scale, especially the potential, um, and kind of the water cycle with it. Where it becomes more difficult is where we start seeing miscanthus that is stressed abiotically or stressed by temperature, moisture, where um, our models aren't currently able to resolve those things as well. And below ground stuff is we don't really understand how that works because we don't have a whole lot of data showing how below ground biomass changes over time. Um, yeah, and with that, I guess I'll take questions.
Thanks so much, Brian. That was, well, I thought it was great. Would you mind stopping your share?
Yep.
Perfect. Okay, please put your questions for Brian in the chat, although of course you can unmute and ask out loud. Um, Brian, I have one to kick us off. How do you think we in those in the industry should be thinking about using models to make decisions for new fields or new biorefineries? How important are models to those decisions?
Well, let me think. That's a tough starting question. Uh, um, well,
I guess maybe let me reframe it, put it more in PhD defense stuff. You're getting a job. Your
yep.
new job is with a company that wants to make money off growing miscanthus,
Yeah.
and your expertise is in modeling. How would you use that to help your company make decisions?
Um, well, first off, I would make sure that well, I would first use the model and try to if we have a data set of yield or whatever variable we are most um, interested in across the country, I would use that to um, evaluate or test the models to see what its average error is. Because I think knowing what you can expect error wise is really important for making decisions. Um, you got to have some sort of uncertainty around it. So I guess my first thing would be to figure out what the uncertainty is of the model first, um, and then go for and try to use it. If that makes any sense.
If I was to paraphrase, you'd be really interested in making sure you understood how precise your model was before making investment decisions that were based on modeling outcomes.
Yes. Yeah.
And how important is data to improving the error in models?
Oh, extremely. I mean that's the only way I mean, good data are supposed to be, I mean, um, real it is the reality and if um, CSMs uh, sorry, lost my train of thought. Um,
But
go
no, that's okay. See, Damien has a different question in the chat
yeah,
too. So there's other ones coming in. Can you see that, Brian,
yes,
or should I read it? Okay. So I'll just read it out loud. So for those
yep.
who can't see the chat, Damien is asking, and Damien, feel free to unmute. Your accent's prettier than mine. How sophisticated is the model for the decline in biomass after peak yield? Are there weather impacts like freezing, snow, or wind that have impacts beyond a simple time-based decline? Also, is moisture and ash content during this period modeled, since those all have commercial implications?
Yeah, great question. To my knowledge of when I think all most CSMs that I've seen use just a simple time-based decline, clock based. Um, I have not seen any model that uses any weather impacts or that uses weather events to predict um, biomass decline. And I think there's a reason for that. First off, it's really no one wants to go out in the winter to measure how many leaves are in the Miscanthus, and you have to do it probably potentially at a pretty high frequency because I think that just a big wind event can then there it goes. Um, so I think um, that's why I think you could potentially, I think we were thinking about you could potentially use phenocams or some sort of automated system to help um, figure out how many leaves are on the stems and how much biomass is there. I think that would be a way of potentially doing something like having a weather dr driven uh, biomass decline function in the model. Also, the moisture and ash. Um, some some models do predict moisture. Miscan 4 does predict moisture. Um, I don't know of any other ones that do off the top of my head. I know the crop model that I work with, Agribus, does not predict crop moisture. Um, and ash content, to my understanding, is ash is you can use nitrogen content as a proxy for that in materials, which most models do have nitrogen content predictions. So those would be modeled. Damien, does that answer your questions?
It does. It does. Thank you. Yeah, appreciate it.
Yep.
A really nice presentation also, I didn't put that in the question, but yeah, really appreciate you walking us through in a really understandable way. It was great.
Great. Thank you.
Are you able to see the questions there,
Yes.
Bryan?
Yes.
Let's go
I
ahead
didn't
and
know. I didn't know if you wanted me to do it.
uh, if you'd like to read them out loud. I don't know actually. I don't know Brad. So Brad, if you are in a position to unmute, please feel welcome to do so. At least I don't remember if I know Brad. Part of our goal here is to meet new people.
Brad Casberg with Argonne National Lab.
Okay.
Yeah, I just had a question about regional or yeah, I mean, I'm not too concerned about full national scale, but where do we feel is the best resource for less precise, but kind of broad brushstroke Miscanthus models for just getting a sense of yield variation within states?
I think the best and what I think is most used is um, was developed from it's called Prism ELM. Emily, if you want to put in the source of that, but to my understanding, I think that I wouldn't consider that a crop model. It uses it doesn't step through time. It doesn't do it just uses environmental variables integrated over time potentially to predict to estimate yield across different regions. Um, I think that's probably a good option. The other option is oh, um, I mean, when I is there are papers out there that talk like some other models like BioCro where they do some regional estimates. So there, I don't know if there's any good like I guess all in one place where you can find all of the yield predictions for Miscanthus from different crop simulation models like an ensemble. Um, but they're out there in the literature. But yeah, Prism ELM is probably the most popular to use.
Thank you. I appreciate it.
I see Travis just has a compliment. I don't see a question in there. Thank you, Travis.
Can I ask one question?
Yes.
Michael Moss. energy limited. Do you work on with your model on other species of Miscanthus or new variety of Miscanthus, or is the model is based only on Gigantus?
Yeah, right now it's just based on Giganteus, specifically the Freedom clone.
And do you think that starting working on the new hybrids is something we should start to do to not be, surprised that we don't know anything about models for those one which are coming?
Yes, yeah. Audie, Carol, they had a really great paper just last year about changing, like measuring different parameters, model-based parameters in these different genotypes, and integrated that into, I believe, Descent. So yeah, and then I know a colleague of mine, Theo Hartman, is also really interested in doing that, on using, making sure that these parameters can be used or can be adjusted based off of easily measurable things from these other new upcoming genotypes.
Thank you very much. Thank you. Very nice presentation.
Thank you.
I'm just going to jump in here. I had some technical difficulties on my computer, so I'm Mike Masters here for a second. So there have been some questions about data. I don't know. Yeah, we have Matt Langholtz on the call, who has used the PRISM data set extensively for the billion ton reports. And I think Matt was actually our very first biomass webinar speaker last year. So I can share the PRISM link, but my computer kind of crashed for a second, but you can find that through the Department of Energy. And then there's another question. Carol, do you want to be, this is probably the last question we'll take today, so I know we're getting at time, but Carol, do you want to be more explicit about the data that you're looking for? If you're in a position to unmute, I suppose.
Hi, everyone. I asked about the parameters, and he mentioned that there are one page or a paper or page where I can find some kind of parameters to modeling my all this data. He mentioned 5 minutes ago or less in one of the questions.
Yeah. So, yeah, if you, every paper, or at least every paper that that talks about developing and calibrating a crop simulation model for Miscanthus normally says what parameters in a table or some way that they used. So I don't think there's any place where you can find all like the universal parameters, because all these models have different structures and have different parameters for each one. So I would say
Makes sense. Yeah.
going to the each individual paper where they talk about those.
I know one of the more exhaustive lists, I think, is in that STIX paper, the STICS model out of Europe. Is it the Struyu paper? There's an exhaustive list of parameters in that paper that's quite helpful.
Yep.
So I want to thank everybody. We are at time for today, but this has been, I think, an exciting discussion and good Q&A. I really look forward to our last our last seminar, which is next week. But please send me ideas that you have for the next seminar series. I would think we'd like to feature some of our European partners more prominently next year. So if you'd like to present, please let me know, and we'll prepare that agenda accordingly. With that, thank you all very much. You can find the webinar links on YouTube, and we'll see you next week.
Thank you very much.
Thanks, Brian.
Everyone.